Hi, everybody. My name is Nicole Wine, and I'm going to be talking about edge minimum walk of modular length in polynomial time. This is a paper in ITCS 2025, and it's joint work with Antoine Amarilli and Benoit Gross. So we're going to start off with a very simple sounding question. Given an unweighted directed graph G with terminals S and T, can we efficiently find an odd length ST walk with the minimum number of distinct edges? This is a special case of the problem that we study in this work, and to the best of our knowledge, nobody had studied this question before. So it may look very similar to some kind of classical problems, because problems that look similar to this about odd length walks and paths and cycles have been studied a lot. And in particular, this problem might look similar to the following problems. In particular, it's not the same as the shortest odd ST path problem. The reason being that in an ST path, it has to be a simple path, whereas here we're considering ST walks, where we're allowed to repeat vertices and edges. The shortest ST path problem is well known to be NP hard by a simple reduction from the two disjoint paths problem in directed graphs. Another problem that this is not the same as is the shortest odd ST walk problem. This problem is easily seen to be in polynomial time by basically making a couple of copies of the vertex set and finding a regular old shortest walk on a new auxiliary graph. But this problem is different from our problem because in the regular odd ST walk problem, you care about the total length of the walk. That is to say, the total number of traversals of edges that you do along your walk. Whereas what we care about is the minimum number of distinct edges. That is to say, if we have a walk that reuses a bunch of the edges that we've already used, we only count each of those once, whereas in the standard ST walk problem, you'd count those however many times you traverse them. Let's look at this example graph to see how these three problems are different from each other. So first, here's what I claim. I claim that at the bottom, this red walk here is the shortest odd ST walk. So this is an odd ST walk. It uses 1, 2, 3, 4, 5, 6, 7, 8, 9 edges along the walk, and it turns out that that's the shortest ST walk in this graph. On the other hand, for our problem, the answer is the top blue path. This is the edge minimum odd length walk. And this walk, even though the walk itself does more edge traversals, it does like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which is longer than the shortest one on the bottom. Even though that's the case, the total number of distinct edges that our top blue walk uses is smaller. It only uses 7 distinct edges instead of the bottom one, which uses 8 distinct edges. Okay, so the point is that these are two different problems. They can have different answers on certain graphs. And let's look at also the shortest odd ST path problem. For that problem, you'll notice that in this particular graph, there's actually no odd ST simple path. And for that reason, the answer would be, I guess, infinity. But you could also imagine adding, an ST simple path of length, let's say 101, and then the answer to the shortest odd ST path problem would be 101. So all three of these problems can have different answers, and those shortest odd ST path and shortest odd ST walk are both well studied, but this new problem, as far as we know, hasn't been studied. So the problem that we really study is a generalization of this, where we care not only about odd length or even length walks, but we care about general modularities. So we care about ST walks of length R mod Q for any R and Q. And the setting we focus on most is when R and Q are constants. So here's the problem. It's the edge minimum walk of modular length problem, and it's given an unweighted directed graph with terminals S and T. Find an ST walk of length R mod Q, which is edge minimum. That is to say, it uses the minimum number of distinct edges. We're studying directed graphs. You could also just study this problem on undirected graphs. We include showing how to solve it on undirected graph as well in the paper, but it's just that it's kind of less interesting on undirected graphs, which is why we are focusing on directed graphs. Okay, so our goal is to study this problem and figure out if there's a polynomial time algorithm for it or if it's a hard problem. And a priori, it seems kind of unclear what the answer would be because you have those two similar problems, the shortest odd ST walk and the shortest odd ST path. One of them is in polynomial time, the other is NP hard. And in particular, this problem seems harder than the regular shortest odd ST walk problem because this is more of a global problem rather than a local problem in the sense that you really care about how different parts of your walk intersect with each other because you want them to kind of intersect as much as possible so that the total number of edges overall is minimized. Okay, so what's the answer? The answer to this problem is that it's solvable in polynomial time, and that's the main result of this paper. We show that you can solve this problem in polynomial time for constant q, and in particular for general q, you can also solve it in this time that we have here, n to the order log q times 2 to the order of q times log squared q. Okay. We also study a few generalizations of this problem. We study the weighted versions, and we also study a multi-terminal version, which also, it turns out, generalizes the directed Steiner network problem. So I won't talk about those specifically. Okay, so my main goal for the rest of this time is to give some ideas about the proof, but only for the special case of odd length walks. That was the one that I introduced at the very beginning. And then I'll say just a little bit about extending it, but mainly I'll focus on this special case. So in the special case, what our goal is to find an edge minimum odd length ST walk. And we're going to call it W in a given directed graph. Okay, so we can start off by kind of trying to understand the structure of what the walk will look like. And the first observation that we can make here is that without loss of generality, this walk W can be assumed to contain no even cycles. And the reason for this is like if you had a walk that did contain even cycles, an even cycle, then what I could do is just go ahead and remove that even cycle. And that would only improve my solution because it would make the number of edges, it could make that number of edges only smaller. And additionally, it's not going to change the parity of the walk because I just removed an even cycle. Now, let me be clear here on what I mean by remove an even cycle. I'm not necessarily saying that I'm removing all of those individual edges from our solution walk W, because those individual edges could be revisited by other parts of the walk. I'm just saying that we're taking that sub-walk that consists of an even length cycle and we're deleting that sub-walk. And we can do that without loss of generality. Okay, let's make another observation about what our walk could look like. So the next claim is that without loss of generality, the walk does not contain two odd cycles in succession. Something like this picture. And the reason it doesn't is because what I can do is go ahead and remove one of those odd cycles and instead traverse the other odd cycle one more time. And this is, again, only going to help me because it's going to only decrease the number of total edges. And it's not going to change the parity because I'm trading not traversing one odd cycle for traversing another odd cycle one more time. Okay, so putting this together, What this tells us is that our walk W that we're looking for can be assumed without loss of generality to either be, could be a simple path, or it could have the following structure. It could be a simple path, which we're going to call P1, followed by an odd cycle, which we're going to call C, and then followed by another simple path, P2. And that's what's implied by both of these two observations. And the structure is somewhat simple, but it's not necessarily that simple because these different components, P1, C, and P2, could potentially like intersect with each other in a bunch of different complicated ways. And that's what we're going to look at next. So it turns out that you can also make some assumptions without loss of generality about how these different components interact with each other. So here's observation number 3. It's without loss of generality, P2 doesn't like re-intersect with the cycle C. And the reason for this is shown in the picture. So first we have our path P1 here. This is our first simple path. Then we have C, which is our odd cycle. And then we have P2, which is another simple path. But a priori, P2 could have intersected back into C. But we can say without loss of generality that it doesn't, because we can go ahead and just remove this section of P. And instead, we can traverse this path here along the cycle itself, reusing those edges. And this is only going to help us because it could only decrease the number of edges. And it could change the parity of the path doing this replacement. But the point is that if it changed the parity of the path or the walk, what I could do would be to go around this odd cycle one more time to change the parity of the path back to what I want so that the whole entire walk has odd length, and then I'm good. Okay, so another structure that we can, without loss of generality, assume doesn't exist is that P2 goes and intersects P1 and then takes like a parallel path with P1 so that P1 and P2 like share some vertex and then they diverge and take disjoint paths and then they re-intersect at a later point. We can assume without loss of generality that this doesn't happen. And the reason is because we can remove this like detour part of P2 and replace it instead with this path directly along P1 where we're reusing those P1 edges. And the point is similar to observation 3, where when I do this, the parity of the path might change, but I can fix that by just going around that odd cycle another time. Okay, so what we've done now is narrowed in on what the structure of this walk could potentially be. And what we can end up concluding is the following. So our conclusion is that the path, the walk, must look something like this. Either it's a simple path or it must look something like this, where P1 is this like solid path here, and then C is this odd cycle here, and then P2 is this dotted path, which could intersect back with P1. It couldn't intersect back with the odd cycle because of observation 3, but it could intersect back with P1, but only in a specific way. Because of observation 4, you can't have any of those parallel paths. And so the only way that P2 could intersect with P1 is like it hits P1 at some point, takes in both P1 and P2, take some common subpath, and then P1 jumps backwards along the path. Sorry, P2 jumps backwards along the path to hit another point in P1. Then again, they take a contiguous subpath. Then P2 jumps back along P1, takes another contiguous subpath, and so on. And this could happen an unbounded number of times. And to clarify, in this picture, these kind of forward arrows don't necessarily represent single edges. They could represent whole entire subpaths that P2 and P1 are agreeing on before P2 then jumps backwards. Okay, so this is the structure that we are interested in for our final walk, W. And now the question is, how do we actually find a walk like this? And what we can do here is use some insight from some prior work. So the prior work that we're interested in here is prior work on the directed Steiner network problem. And this is work by Feldman and Rule and in 2006 and Feldman and Marks in 2023. And interestingly enough, these are two different Feldmans. And what they showed was that what you can do for the directed Steiner network problem is to bound the undirected cut width of the solution and then use dynamic programming. And what this means for our situation, for our problem, is that we can solve the problem by bounding the cut width of the underlying undirected graph that consists of the union of edges in our walk W. And then we can use dynamic programming on top of that to actually find such a walk. So let me tell you now what cut width is. So a graph has cut width at most C if there's an ordering of all the vertices in the graph, so that for every point along that ordering, I, there are at most C edges that cross over that cut. So at most C edges with one endpoint less than I and one endpoint at least I. So as an example, let's take a look at the graph that we just figured out must be the structure of the walk that we're looking for. And it's visually clear that this graph has a small cut width, because we can say, well, let's look at the ordering of all the vertices according to like the horizontal order of how they appear in this picture. And then if you look at any vertical cut, for example, like this, you'll notice that only at most 3 edges actually cross this cut. And that's the important property that we need in order to do dynamic programming. And to clarify here, what I mean by cut width is the cut width of the underlying undirected graph. I'm not interested in how many times the walk itself crosses over the cut. I'm interested in take the union over all of the edges in W and then take the underlying undirected graph and then ask how many times that thing crosses the cut. Okay, so the point is that how we solved this problem, in summary, was to first get a bunch of kind of structural lemmas about how this walk can look without loss of generality, and then say we can bound the cut width of the walk, and then we can end up using dynamic programming to actually find such a walk. Okay. So that's the idea of the proof for the odd length case, which turns out to be, relatively simple. The real kind of issue here is extending to general length paths or walks. So what we would like to do is extend to general R mod Q. That is to say, we want the length of our walk to be R mod Q instead of just, being odd. And let me say a few things about kind of a few issues that come up when you try to do this. So the first observation you could make here is that if your walk W has a cycle of length co-prime to Q, then the argument looks pretty similar to the odd case, and it's not too difficult. The reason for that is because if you have a cycle that's co-prime to Q, then you can make arguments that, like, without loss of generality, certain other structures of the walk don't exist, because what I could do would be to like delete those certain structures of the walk, and to compensate for the fact that the remainder might have changed, I'm going to just go ahead and traverse that cycle of co-prime length to Q as many times as I want. I can do that for free. And because this allows me to reach all of the possible remainders, since it's co-prime to Q, this allows me to significantly simplify the structure of like the rest of the walk in a similar way to what we did in the odd case. Okay, so really the issue here is that there could be like many different cycles with different remainders mod q, and all those different cycles could kind of intersect with each other in intricate ways. You know, if q is equal to 24, you could have a cycle of length 8 and another one of length 6 and another of length 3, let's say, and they could all kind of interact with each other in different ways or be nested. And still what we want to do is bound the cut width of such a walk. So the question that arises is like, could the walk have high cut width by, for example, having some kind of structure emerge that looks sort of grid-like, which would be a high cut width structure? And the answer that we show is no, this couldn't happen. And so we can again bound the cut width and then use dynamic programming to solve the problem. But the structure turns out to be kind of a lot more complicated than just the odd case. And kind of a general overview of kind of the structure of the proof, which I won't go into any details, is that when the walk W witnesses like certain intersection patterns, more remainders become achievable. And for that reason, you can kind of bound the total number of certain intersection patterns that could happen, because as soon as your walk can achieve all possible remainders, you can use a similar argument to the coprime case, where you can say, well, the rest of the walk has to be kind of without loss of generality, pretty simple, because I can already achieve all possible remainders with the part of the walk that I've developed so far. And because certain intersection patterns mean that the number of remainders that you can achieve are increasing, then you can only have so many of those certain intersection patterns. That's what we show at a high level. And then lastly, the final goal is to bound the cut width and then use dynamic programming. And kind of it helps to be able to bound the number of certain intersection patterns in order to bound the cut width. And one more thing is that in contrast to the odd case where it was visually clear what the cut width ordering should be, one of the issues with this general case is that you actually have to define what the cut width ordering is going to be to witness a small cut width. Okay, so that's all I'll say about the proof. Now let me finish with some open problems. So one open problem is just improving the running time below what we got. So this is our running time, and what you'll notice is that there's a q here in the exponent, and this is not necessarily needed, potentially. So you could imagine getting a running time that only had like factors of log q in the exponent. So that's one direction. Another direction is to explore this problem, which we think has been unexplored. We didn't find it in the literature, which is sort of similar to the problem that we've studied. It's given a number L, find an edge minimum ST walk of length exactly L. This is different from the problem we study because we want one that's length R mod Q, and this is saying length exactly L. And what we want to do is do that faster than the trivial algorithm, which would be in time n to the power of L. Another possible direction is that you could kind of look at intermediate problems between shortest walk and edge minimum walk, because in shortest walk, you have to pay every single time you traverse an edge, whereas in edge minimum walk, you only pay up front once. And so you could imagine some kind of cost structure that was somewhere in between those potentially. The last open problem that I want to mention is generalizations that are related to regular path queries. So it turns out that this is actually the original thing that kind of brought this problem to our attention and made us want to study it, is that it turns out that in database theory, oftentimes you're looking at a graph where edges are labeled with certain characters and you're interested in paths or walks through the graph. that match certain regular expressions, and saying that a path it has remainder r has length r mod q is like one special case of that type of regular expression problem. And so you could imagine various generalizations of the problem that we studied to certain regular expressions. And you can read more about that in the paper. Okay, that's all. And thank you all for listening. If you have any questions, feel free to email me.